A very warm welcome to the students. Today we will discuss about the VI characteristics of a PN junction diode under forward bias and reverse bias. So first of all, let us see the definition of a forward bias. A forward bias is such that the potential of the junction of P, that is denoted by Vp, should be greater than the potential of the junction N, which is denoted by Vn. If this is the case, then we have seen that the current through the circuit I is comparatively more than the current in reverse bias. So we can say that the resistance in forward bias is low. Now let us see what is the definition of reverse bias. The definition of reverse bias is when the diode is connected such that the potential of the junction P, Vp, is less than the potential of the junction N, denoted by Vn, then the diode is said to be connected in reverse bias. We have seen that whenever a diode is connected in reverse bias, then the current flowing through it is very low. So we can say that in reverse bias, the resistance offered by the PN diode is very much high. So let us now see this in form of a graph or plot. So here we have plotted the current as a function of voltage. So the abscissa denotes the voltage, the right hand side denotes positive voltage and the left hand side denotes negative voltage, and the ordinate denotes the current. In the upper side, the current is I forward, which is in the order of milliampere, that is of the order of 10 to the power minus 3 ampere, and in downwards the current is reverse current, which is of the order of microampere. That means the current is of the order of 10 to the power minus 6 ampere. So now let us see what happens in forward bias. Under forward bias, as we increase the input voltage, the current increases very slowly. That is, from point O we can see that the current increases very slowly to point P. Now the question is why? It is because as the voltage increases, the depletion region decreases. Now with the decrease of the depletion region, the current first increases slowly up to a particular voltage called threshold voltage, denoted by VTH, whose value is around 0.30 volt for germanium and around 0.70 volt for silicon. After threshold voltage, we see that the current increases exponentially from, let us say, point P to current Q, to point Q. Okay. Now we see that the slope of the VI curve is not constant, is varying. So we can say that the resistance R in forward bias is also not constant. That is why the resistance offered is called dynamic resistance, denoted by RD. Sometimes it is also denoted by RAC, whose formula is the change in voltage delta V divided by the change in current delta I. Now let us see what happens in reverse bias. In reverse bias, as we increase the voltage, the depletion region increases. Now as the depletion region increases, there is no substantial current in the circuit, but due to the thermally generated minority charge carriers, we will see a very small current denoted by O, let us say to point R, from O to point R. Now this is called reverse saturation current. This happens up to a particular voltage called breakdown voltage, denoted by VBD. BD for breakdown. Now as the input voltage increases, breakdown voltage, or as the input voltage becomes more than the breakdown voltage, breakdown takes place, as a result of which the current in the circuit suddenly increases substantially, denoted by RS portion in the plot. Now here we have seen that the delta V, that is the change in voltage, is very small compared to the change in current delta I, which is large. Now we will use this in application of diode. So we are seeing the application of PN junction diode as a rectifier. First of all, what is a rectifier? It is an instrument which converts alternating current into direct current. Now the working principle is, we have seen that a diode under forward bias offers a very negligible or low resistance to the input current, and a diode under reverse bias offers very high resistance to the input current. So if an alternating voltage is given to the diode, it cuts off the negative cycle of the input voltage and only conducts the positive cycle of the input voltage. We will use this principle as rectifiers. We will see two types of rectifiers, which are half wave rectifier and full wave rectifier. So in half wave rectifier, we have fed alternating input voltage denoted by Vi to a PN junction diode, which is followed by a load resistance, and thus the circuit completes. So what happens is, we have plotted the input voltage across D. Now what happens? This is the alternating input voltage. The blue portion, as signified here, is under forward bias with respect to the diode D. So it will be conducted through the diode, and the output voltage will be found along or across the load resistance RL. Now for the negative portion signified here, the diode is under reverse bias, so it will not conduct. So in the output we will get a very low voltage which is very negligible, so we will consider it as 0. Again in the next cycle, when the input voltage again becomes positive, the diode will conduct and we will get a similar output voltage. Again when the input voltage becomes negative, that is for the negative half cycle of the input voltage, the diode becomes reverse biased and will not conduct. So here we have seen that only half of the cycle of the input voltage is fed across the output. That is why it is called a half wave rectifier. But in a full wave rectifier, this problem is eliminated by using a second diode in the lower half of the circuit. So here we have two diodes, D1 in the upper hand of the circuit and D2 in the lower hand of the circuit. What happens when the input voltage is positive in the upper hand circuit? It is denoted by, here it is the green, denoted by the blue one. Then D1 is positive, and D1 is, the voltage across D1 is positive, means it is under forward bias, so it will conduct current through it, giving output voltage, which is the blue one denoted here in the output voltage. Again in this time D2 will not conduct. Now what happens is, in the negative half of the cycle for D1, D2 is forwardly biased, so it will conduct and we will get the voltage in output. Again, in the next half of the cycle, D1 is forward biased and D2 is reverse biased, so D2 will not conduct, D1 will conduct. Again, in the next half of the cycle, D1 is reverse bias and D2 is forward bias, so D2 will conduct. Thus we see that here we get the full wave of the input voltage. That is why it is called a full wave rectifier. I hope this will make you understand about the working of a PN junction diode as a rectifier. Thank you.